lunch. I hope you had a good lunch. Better than what Dan got us. So as we left off, I had just said make a block, and I gave it the name square. And here we are in the block editor, which is this little window here. And you see a hat block that has in it a block square. And what this is supposed to make you think of is the way hat blocks work is they say, when such and such happens, like when the green flag is clicked or somebody pushes the space key, do this script. Well, this is when somebody uses the square block, do this script that we're about to write. If we go to the motion palette, down at the bottom, you will see that there's a square block right here. That's the one that we're making, but it's already there in the palette. So to draw a square, what we have to do is draw 4 sides. So I'm going to say repeat 4. Control, yeah. And then back to motion. Move 10 is too small. I'm going to say 100 steps. And then turn right. And of course, that has to be for a square 90 degrees. Baker says, wow. Latency way down now. Oh, good. Awesome. Dan, you did the right thing, whatever it was. OK. So there's my square block. And now I'm going to make a little script. I'm going to say, when the green flag is clicked, put the pen down and pull up my square block and stick it in the script. So when green flag clicked, pen down, square. Now I'm going to go click the green flag, and there's square. And let me edit it if I, oops, command click, edit. So you can see everything at once. The square block's definition down here in the block editor, and the script that uses it when green flag click, pen down, square. And here's the square, which actually is a square on the screen, even though on Dan's computer it's kind of a squished rectangle. OK, now that we have this square block, we can do more complicated things with it. So for instance, I can say, repeat 10 times, draw a square, and then back to motion, turn right. I'm going to just pull out a random number, 36 degrees. Somebody got it. Dan got it. Okay, I picked 36 because 10 times 36 is 360. So we're going to go all the way around. Now I click the green flag, and we get this beautiful picture. OK? So this is old, like 50-year-old logo stuff. No, 40-year-old logo stuff that I'm doing. But what's cool about it is, again, this visual presentation of the square block. So in the block editor, there's this thing that says, when square block used, do this. Repeat 4, move 100, write 90. So I'm going to clear the screen now.
Do you want to check and make sure everybody's got that?
OK. How did I just clicked the clear block in pen.
I'm seeing.
OK.
One thing you might be able to mention, in the block editor, you change something. I found this out last night. You change something in the block editor right now and try to run it. It's not saying until you close the block editor. Right?
Yeah, you have to say OK to your changes. Yeah. OK, so. Yeah.
Say OK, and then how do you...
All right, so how do you open the block editor? Well, here's the square block right here. And I'm on a Mac. I command click. Those of you with some other kind of computer can right click. And then you choose edit. And here's the block editor with square. Now, I don't like this block because it always draws the same size square. So I want my block to take an input that says how big the square should be. So in the block editor, if I hover over the word square, you'll see, I hope, 2 orange plus signs, one to the left, one to the right. And you can click on either of those to add something. I'm going to click on the right one. And I get this little dialog that says create input name. I'm going to create the name size. Okay. So now, right. Hang on, I'm gonna. I don't like. There we go. So now, inside the block editor, the block that's inside the hat block, instead of just saying square, says square, and then there's a size little variable blob. This is just like if you say make a variable in Scratch. One of the things you get is this little orange blob that you can use in scripts. So I can use size inside this script, and I'm going to grab it and move it into the move block. So instead of move 100 steps, it's move size steps. And of course, it's still repeat 4, and it's still write 90, because we need those things in order for it to be a square. Those things are part of the definition of squareness. But now it can be a square of any size. And if you look up here, you see that already I have a slot in here. So now, when I run my program, I can say 150 and get a huge picture. And then I can change the pen color. Did actually that work? Yeah. And now I can say 50 and run it, and I get this little picture. So different size pictures, different size squares. Or maybe it'll be clearer if I just take the square block by itself. So here's a square of size 50. And here's a square of size 100. Here's a square of size 150, and so on. Okay? So that's how we make blocks and how we make inputs to blocks. Now that we have this, we can teach our first big, powerful computer science idea of 2 in the course, namely recursion. Okay. Where did my pile of forms go? Here they are.
All available online, so if we want to watch parts of it again, we can.
I'm going to hope to put this all online.
Yes, no, no,
Either live or
yes,
so
no,
this is the only thing we're going to have.
yes, some, and no. Okay.
Lecture. These are all online already.
So from the forms here, sorry, Dan, for moving out of the video. Okay. From the forms here, I see that a lot of people are new to recursion. So I'm going to start at the very, very beginning. And the very beginning is, I'm going to open, not save the current project, examples. So click in the File menu, click Open, and then click Examples on the left here, and then open this Examples folder, and down at the bottom, pick V. V-E-E. All right, so it's V. Yep. Double click examples and then click V. Who's with me?
We're there.
You there? Okay. So this is the first lesson on recursion. It was invented by my friend Paul Goldenberg, the world's best teacher. It works like this. I'm going to click the green flag, and you guys watch what the sprite does. Click. 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 So what we're getting is always the same V shape, but with different decorations at the two top ends of the V. So are we, you guys okay? Nope. Okay. So right now, there's a star on the left here, and there's a square on the right. And the decorations that are chosen come from this list. This is a scratch list. And the elements of the list are hex, square, and star. And those are the things that get run. So how does that work? Let me show you the V block by editing it. So here's the definition of V. It says, turn left 45 degrees, move forward, and then here's the interesting part. Run item any means choose an item at random of ends. So pick one of these blocks and run it. And so that's where this star came from. Then move back, turn right, move out, and then again, run a randomly chosen one of these things. Then move back and turn left so we're facing straight up again. Okay? Is everybody happy?
Once you go there one more time, I think.
Yeah, one more time?
Yeah, just one more time.
Barbie had a question.
No, under M's, if you just drag in, that's just the scripts for how to make hex, how to do it.
Yeah.
You can show one.
And so-
It's just like square, except different angles.
And so this is another one of the advantages of BYOB in that you can put more than just a line of text.
Yes, one of the advantages of BYB is that we can put blocks in a list. Yeah. When I'm doing this with kids, I don't even say anything about that because that's a later topic. And you know what? Kids just take it in stride. Never a problem. Okay, so back to the presentation screen. Run the thing, run the thing. Okay, and now I'm going to make a slight modification to the list ends. I'm adding V. I actually added V twice because I like the probabilities better that way. So, class of kids.
Which menu was V under?
It's blue, so it's motion. But what I did to add it to the list was I clicked up arrow because I have my script set up so that up arrow adds it and down arrow takes it away. So class, what's going to happen when I push the green flag? Draw a little picture on a scratch paper of what you think is going to happen. Hex, square, star, and V are the possibilities for what we put at the ends of the V. So what kids draw typically is a picture that looks like this, and then there's another V out here with something. Okay? So I'm going to go ahead and click the green flag. Just like before. So this is like what a kid typically guesses. That you get a V, and there's one more V at the end here. And then I click it again, and this happens. And all the kids say, wow, I didn't expect that. And I just keep going.
You should hide the list ends.
Eventually, we get to something like this. And, at this point, kids are all, wow, how did we get that? And the point about this demo is it's the same trivial little 8-line program that we were using before that was just drawing the plain old simple V's. But the fact that the block V can now call itself gives rise to an unending realm of possibilities. That we can get enormously complicated pictures like this out of the same simple program. And that's the power of recursion. Okay, so now go back to being adults. One of the nice things about doing it this way is that I was able to introduce recursion while completely finessing the issue of base cases and how does the recursion end. Because in this case, the ending is probabilistic. Right? In principle, we could have it go on and on forever and never stop, but in practice, that never happens, and so everything's cool. And then later on, we can go to more traditional examples. Some people like to introduce recursion. I'm talking to you now as teachers. In a few weeks, maybe 2 weeks, you'll get to this material in your role as students. And you have to think as you're doing this sort of with two hats on, your student hat and your teacher hat. In the teacher hat now, I want to say it's very, very common for people to introduce recursion with very trivial examples. Okay, so to give you an idea of what I mean, Baker has raised hand. Yes, Baker?
That's cool.
Oh, and except I can't hear anything because my speaker's muted. How did I add V? Oh, okay, thanks.
Sorry, I guess my mic is on. I could have asked it live.
Yeah.
With major echo.
Major echo. Okay. How did I add V? If you look right here, it says when up arrow key pressed, and then this is like way ahead of where I would want to be with the kid at this point, but I look at the length of the list, and if it's less than 4, meaning there's just hex, square, and star in it, then I add V twice. This add block is one of the standard Scratch list blocks. And I'm saying add the script V to ends. So the script is the part that I haven't talked about yet. That's the next big idea, is the one about higher order procedures. For the down arrow key, if there's more than 3 elements, just delete the last 2. So that's how I did the adding.
It's not lagging anymore, just for your.
It's not lagging anymore. Awesome. Yay. Okay. So I'm going to now start a new project. I'm not going to save this because it's already saved.
I have a proposal. We just set up headphones, which you don't have to wear, but if someone raises their hand, you can unmute and hear them without the echo.
What I'll do,
Can I try that?
yeah, sure.
I don't know why that's broken. Oh, here, that.
Okay, you're going to plug me in. What I'll do is wear it this way,
That's perfect, yeah.
and now I can hear myself.
Ask everyone remotely, not here in the room, but talk, and you can hear, you should be able to.
Okay, so everybody out there in TV land can talk to me.
Is it working?
Well, I'm hearing myself delayed, which makes it hard to talk, just like if everybody else hears me. Okay, so you guys, if you want to talk to me, can do so.
Hear anything?
Okay. All right, awesome. I'm going to turn the volume down because I hear you guys really loudly. Okay, there we go. Now, so this is what I think the bad way to introduce recursion. We make a block. It's going to be motion, command. Let's see, what's simple? Square. Okay, so I'm making a square block. And it'll have an input called sides. It's
Variable, and then make block.
and then I'm going to say if and I get a greater than block.
right?
If sides is greater than 0, move 100 steps, turn right 90 degrees, and square sides minus 1. So this is a recursive procedure to draw a square. And let me click OK on this, and I'll bring it back up on the editor in a second so you can see it. But meanwhile, I want to show you how it's used. Namely, I would say square 4. Oops, pen down. Okay, and this draws a square. And I'm show the code again, yeah. So here's the code.
This is your standard.
Yeah. So remember that what we're looking at here is an example of what not to do as a teacher. And that is show kids, quote, simple, unquote, recursion in which the very last thing in the procedure's definition is the recursive call. Okay? And the reason not to do this is that if you do, every kid will think will mean that recursion means go back up to the top. Right? So it's as if you were writing a loop. And it's true that you can use recursion as if you were writing a loop, and that's what this does. And it's true that it's simple, but it kind of guarantees that kids get the wrong model in their heads.
Okay,
It's under Bank of Brian.
Yeah.
just trying to recreate what you do right now, so
Mhm.
if we could slow down a little bit.
I'll help you get there.
Well,
I put my block under variables and not under motion.
It doesn't matter where you put the block. It just affects what color it is and what and where to find it. Yeah.
They're trying to now edit the thing they just made.
Yeah.
Square.
So I mean, the other issue with teaching it like this, which of course I've done for 10 years, is that they get really good at this kind of recursion. And they can't think through any other kind of recursive problem.
So the V example that I started with is a branching recursion. There are two different recursive calls. And there's no way to think, go back about that and make sense of it. So start with hard examples. It's sort of the counterintuitive thing that I'm saying.
No, that's interesting.
Well,
Because
I think the argument that I've done is that when we were teaching only scheme, I should go into so when we were teaching only scheme, in the scheme world, we would teach first this simple kind of a thing. But it wasn't, scheme was a functional language, so we didn't do, this is a side effect thing. We were supposed to do something, like draw, put the pen down, do something. We were doing something like calculate Fibonacci or factorial or something like that.
Oh,
And-
maybe that's what you were doing.
Well, in scheme, in
In
early
scheme.
hello scheme, it's first count the sentence and that kind of stuff. And then
Not when I'm teaching it.
it's these three?
Yep.
Okay, well, we
The
do.
very first recursion
Count
is
change or
down up or count something. Yeah, it was something branching.
Okay. So,
Tell us.
Yeah.
so my story is that we would start linear recursion, which is this, which you only have one recursive call, and then we get to the point where you have tree recursion, where you have two or more recursive calls. And then you end up having exponential growth for the whole thing, and you can't do Fibonacci of more than 10 or 20 because it just grows, it doubles the number of calls you do every time. It's crazy. So I argued that the beauty of having BYOB and Python and other languages that have other control structures other than just recursion is that you can use recursion only when it kind of makes sense. So I have taken to the feeling of, in teaching BYOB, teaching beauty and joy of computing, only using recursion for tree-based recursion. So I would never have done this,
When you
ever,
use
ever,
it,
ever.
right,
My
right,
students
right,
don't even
right.
know you can do this because I would use a for loop.
Yeah.
Because it's there. That's how people think of it.
Yeah.
So you'd use the repeat or for loop or while
Right.
for that kind of a linear thing. And whenever you want to use recursion, you better have 2 or more guys in there. That's how my students think. They've just never seen it. I never say you can't do it with one. I just never show it with one.
Well, actually, 2 or more guys is not really the issue. The issue is that the recursive call can't be the very last thing. You can have
So that's another-
interesting examples where there's do this, do this, do this, recursive call, do this, do this, do this. And that's good enough so that you can't think go back about it.
I
Yeah.
have a question. Last night I was trying to bone up and get myself ready for this. And I started thinking, I said, we never talk about what's actually happening on the stack, at a low level, right? You don't want to do
We
that?
don't ever do that.
You don't want to do that.
I didn't say that. We haven't.
But so wouldn't it be more understandable if you would talk about what's going on the stack? If you try to describe it?
So the question for the people out in TV land was, wouldn't it be easier for students if we talked about the stack and what's going on when you do recursion? I'm reluctant to do that because in fact, it's not true. In a language with higher order procedures, call frames are not stacked. They're stored in the heap. And so that model that you have in your head
Way to get back.
is wrong.
That's the way the stack would do it for you.
Yeah.
So you don't want to talk about low-level stuff.
But also, I think it's the wrong way to do it. If you want to talk about what's going on in the computer, here's what's going on in the computer. Inside your computer are a whole lot of very little people. And each little person knows how to do one block. So there are little people who know how to do move, and there are little people who know how to do if, and there are little people who know how to do turn, and there are little people who know how to do the blocks that you write. So there are square little people, and there are V little people in my previous example. So when you're running a recursive procedure, some particular little person, Sam, is doing it for you. And then Sam comes down here where it says square sides minus 1. Sam's sides is 4. So Sam hires Melissa, who's a minus person, to do sides minus 1 and get 3. And then Sam hires Sally, who's a different square person, to do square of 3. That's what's really happening in the computer. Okay. I say that out of 40 years of logo experience.
I teach it by saying you're hiring people from the square company. And when you get the recursive call, you got to hire somebody else from the square company. So they're different people.
Yeah.
They all work for the square company, but you're hiring different people. That's how I think of it.
And the general principle of which this is an instance is you want to work at higher levels of abstraction first. And in our curriculum at Berkeley, we start here and we work our way down. So at this point in our curriculum, we're not even thinking about how efficient something is. If some block takes exponential time, fine, it does. And then we go to 61B, where we say, okay, now we're going to think about the efficiency of algorithms and what steps the computer has to take to carry them out. And then in 61C, we start talking about things like stack frames.
Third course for me.
Yeah. Now, sometimes some kid will ask a question like what you asked about stack frames, and I will say, okay, everybody in the class except him, put your fingers in your ears. And then I'll say, well, it isn't really like that. Here's what it's really like. Okay, and then go on with class. That does happen a lot, because some kid who, was taught by their electrical engineer dad is thinking from the bottom up.
And remember, I learned it by learning Pascal that you don't like, right?
Yeah, right. Yeah.
This doesn't do, the script doesn't do anything. I mean, it just makes that simple square.
It makes a square, that's it.
That's it.
Just like, well, I wrote
You
it.
would think would do concentric squares or something.
No, it just does one square.
If you want to ever, if you hold this down and then drag this up, you can zoom in. So it's a
Ooh.
very case where
Yeah.
for the remote people, you want to show some stuff, you can do that. And
Okay.
that actually helps a lot. Just hold that down in 2 fingers. That's really very
Ooh.
Barbara, your point though.
Yes, Baker.
It draws a line. Your point is a good one. I mean, what you're saying. What it does is draw a line into
So, teacher,
and it gets called 4 times.
what do you say to the student who asks?
It did it 4 times. It did it 4 times. Square is a misnomer here, actually.
Yeah, it's a single line, and then it goes back up again. The clock is-
Why does the sprite always end back where he started? Oh, that's interesting. So Baker wants to talk about turtle geometry. Adobe Connect quit unexpectedly. Shall I say report? Reopen.
But you might have to restart the whole thing.
Uh-oh.
I should
So in
pause
other
the
words,
video.
so, I mean, the size is equal to 4. So then the condition of the if statement says, okay, if size is greater than 0.
I hate computers.
You do these things. The last thing that it does is it calls a square again.
That's
So
really
then
cool.
it subtracts 1 away from that square
Something-
that it calls. So now square is equal to 3. And it goes back up again, and it comes back down again.
I do have a
So it
window
does it
here.
4 times.
All right, so say share my
Well,
screen.
the question is, we're trying to, see, I said allow everyone. See, allow everyone, is
Yeah.
not to say,
Right.
unless,
In other words, it draws one
Eating
line
access.
through. Okay, it moves here, it turns back.
No, see,
And it calls itself, so it comes back up here again. But it subtracted 1 away
So
from
annoying.
it before, so now it does 3. This thing is 3,
access.
3. It comes down here.
well, no,
and does it
well,
again.
that's different.
Okay, and then it draws a second line. It comes down here and it calls, and subtracts 1 away from
Are you
the square,
still-
now square, I mean, size is 2.
Ah.
Comes back up
They're
again.
restarting Connect
Now,
now.
and they hate me.
Greater than 0, so then it does this again.
Who hates you?
Well, can you hear what he's saying? Is he-
No, I don't hear anything.
Oh, you don't hear anything?
Do itself 5 times.
Are we in this?
Probably still-
Should we-
Ah,
see the difference.
there we go. Yes, I hear somebody. Is that Jeff?
It's still looking
So Jeff is here.
This is Baker talking. Okay, great.
because it's just because
Yeah,
every time you go down
Dan
here,
is not clicking on share my screen yet.
Every time it goes.
Here we go. Share my screen.
Then you get a different
Oh.
thing. You
Wait, so you're telling me to
But
go.
you,
to a
earlier you
square
had
4
said
times.
share my,
tell them that.
Share my. Okay, Baker, can you see now? Anything?
But the path is it makes that line and stops at the vertex, right?
Click share my screen.
I
No.
did, I did.
Right, and then makes
did.
that-
Didn't it ask you about window or
No, no. Oh, there it is. Okay, sorry.
application? Scratch.
So just tell them, it doesn't
So we only put 3 in
Okay, here we
there,
are.
which make
Ask me to they're back in.
Okay, hello world.
correct.
Can anybody hear me in TV land? Uh-oh.
All right, the line, we gotta clear it.
Oh, I see.
Okay,
Got the idea?
so it made it you.
It made it you. So you want to do it 3 times.
What?
Tell it 7 times.
Oh.
It's still the same square. You have to do something else.
You gotta change the angle.
What am I doing?
Just,
wrong? Oh,
just touch it. Just touch it. Just
Okay.
touch it to get back.
Yeah, but that's not where I want to be. I want to be here.
No, no. Oh, maybe that is. I don't know.
Hello?
And 1 time.
Right, in other words, you can add
No.
another variable to your
So you
square.
could make an isosceles triangle if you wanted to, or whatever.
Should they call it shape, not square? It's not really
What are you looking for?
The screen where I can control the.
Oh,
Yeah, well, that's, I mean, now you're talking about.
Maybe there isn't one.
I don't think there is one. It was back in here. It was back in here.
Okay.
Which is down here now.
Which is down here now.
If you think it's easier for the kids to
It's that one. That one. That one. Click. Just click.
I did.
necessarily
And click.
something
And that's it. That was it actually.
That's
yeah.
it.
with 90-degree.
Yeah, so there should be
So
lost audio. Yes, I know. I lost your audio too. Hmm.
that.
You can do. Try to revisit the closed tabs or something. Remember the.
Before, it's always gonna be a square.
Meeting information.
That one.
To make something else with a square, you'd have to change.
Ah, I hear some audio now.
Oh,
Enter meeting
It
room.
just depends on what you want to make. So your point is well taken. So you got a square.
What?
try it.
Okay.
Scratch.
You change the
Okay, my screen is being shared. Okay, good.
Okay.
Audio. Click. Wow.
So it doesn't-
Okay, do you hear me now, Baker?
Polygons and stuff.
If it's bigger than something, if it's.
You can do that, all right?
Yeah.
Right, you can't just.
Okay, awesome.
You back, now go back
Yeah,
to
so
your.
now I can go back
So
to,
if size
oops,
is less than zero,
What's the size?
right here.
hello?
No, you hit it. You hit it. You keep when you hide it. It doesn't show it. It's not just this guy. This guy.
Okay,
This
and
guy.
that's that number that I put in.
All right, there we are.
So if I put in 10 and I change the angle, it's gonna be a radical.
Okay.
Yeah.
Okay, class.
See how she's learning. She just made a triangle. Look at her. Hey,
Right.
hey, Dan, look at this. Hey, Dan. We gotta have you over here. Come over here. Come over here.
Okay, ladies and
Oh, wait,
gentlemen.
the light bulb, there's an aha.
What?
There's an aha. Celebrate the aha.
Okay, aha. All right.
Square, it should be called shape.
Should be called shape, except it always turns 90 degrees. So the only shape it can make is a square.
It's confusing to call it square, because you automatically think of a square as a square. It's got a definition, right?
Yeah.
So what you're gonna draw is something, it could either be a closed shape or not, depending on the number of angles.
Number of sides,
Let me
yeah.
add something, let me add something what he said, but in his procedure itself, okay, he has it set at 90 degrees. What you're saying is if he had another, if he passed another parameter besides size, you pass a parameter called angle, and then you put,
Yeah.
you put, instead of having 90 degrees,
Talk to him,
you
talk to him,
put
talk
the
to
angle
him.
that they pass,
Okay.
and what you're saying is correct. But
Wha-
the way he has his
what's Dan
code
doing?
written, it's always gonna be a square because it's 90 degrees.
Oh, well.
But if,
But it,
but if you
the
change,
block
Dan, what are you
itself,
doing?
I don't think.
he thinks that when when we restarted it, it lost the. It says it's bad now again. It's slow again. So the things that we
okay,
changed.
see here, it's not sure. Are you
Okay, what did you change?
I did change.
No, remember when we updated?
Yeah, I know, but what did you change?
It would be
let's do
called.
this.
It was the connection. So now we're gonna go to book to tool. What was the thing? History. This
Here
guy.
you go, I made a hexagon.
All right, see what I'm doing?
Yeah, that's the one. Okay. I
Okay.
did this.
Here,
Meeting.
down in here. All right?
Preferences. Screen share. That was the setting I had. It remembered
Okay.
our setting.
Now what you're saying is to, now you can change
Same
the
setting.
name of it.
Done.
Oh, that should.
Okay.
So go back to your thing and you should.
Yeah.
Okay, I get it.
All right. So,
Then you might change, you want to change the name of the square, that's why you change.
so people here in the room, for those of you out in TV land, are complaining that I really should have done this. Instead of turn 90 degrees, oh, no, not that. I should have another input called angle
That would be a good way to teach kids that the angle is the
and turn, oops, that many degrees. And now I have a general draw any shape thing. So it can be 3, oops, no.
Yeah, because I teach kids that.
It could be 320. That didn't work, did it? Let's edit this. Turn angle.
Yeah, let's see what polygon it has.
Size minus 1. Oh, whoops.
What should the angles be? They'd have to
No.
all right? They have to know that, right? So in other words, you can just give them the code, all they have to do is change it.
The other thing too is they've gotta be, I don't think the right word is equilateral, but all the sides have to be the same size because we haven't said make it different sizes. But it theoretically,
There.
would say each side should be.
So I made a triangle, and if I change the numbers a little,
70,
I can
plus 10.
Each time,
Yeah.
each time it went through,
Yeah.
make a pentagon,
to your, see,
and so on.
to your side, each time it went through.
Okay, can we come back together? All right, hi gang. Sorry for all the technical difficulties. So what we're doing is talking about introducing recursion. And of course, the canonical example of recursion, I'm going to start a new project, is to draw a tree. So I'm going to make a block. And I'm going to put it in pen because I want it to be a color other than blue. I've learned this. Tree. And then level. And then size. And in order to draw a tree, what you do is move size steps and then turn left, otherwise known as counterclockwise. 15 degrees is fine. And now I'm going to pick up a tree block and say tree, and I'm going to go to operators and get level -1 and a times block and do size times, let's say 0.6. And then I'm going to turn some more in the other direction, right, in other words, and I'm going to move more than 15 degrees. 15 degrees would get me back right side up, and I'm going to turn 20 degrees further than that, 35 degrees. And now I'm going to duplicate this block and put it down here.
Right, make sure you pause. People
Yeah.
Okay, I'll pause. Okay, you want me to zoom in a little?
finish the thing. Finish the thing. It's easier to finish.
Okay, all right, I'll finish it.
As a operator. But it doesn't really matter how they call it, what they call a block, whether it's an
What?
operator or a command.
And it does matter that it's a command.
It's command, but how did it get to be green then? That was,
Oh, it was green because I put it in the pen menu.
okay,
Okay, so that's not.
yeah, but that doesn't really,
Yeah, shape and color are two different things. The only reason I picked a different color is if you look at my script, the recursive calls really stand out.
okay. You just did it for a visual effect.
Yeah. Sorry?
Where did he get the?
Okay, I'm going to stop as soon as I do this. This is where I'm going to stop. And I'm going to use Dan's little zoom me in trick. I know I do. Hush.
You can go all the way. Zoom all the way.
This is good enough.
Close the screen.
What?
It really helps for
Okay.
the video.
All the way. Zoop. Yeah. I may be dumb, but I'm not wicked dumb.
Very happy now.
Okay? So here's our script. And it says move some amount, turn left a bit, and then draw a tree. Colleen did this on Monday, so a lot of you guys have seen it before. And then after I've drawn my little tree, turn right 15 degrees plus 20 more degrees, and then draw another little tree, and then turn left 20 degrees, so I'm facing straight up again, and then move minus size steps, and that'll get me back to my initial position. And it's really important when you're doing fractals like this that at the end of the script you be back where you started from.
You don't have to put a zero in that,
What?
and the move block is zero minus sign.
For the minus size, no, you don't have to put a zero, it just assumes that.
Copy that tree, that first tree block at the level -1.
Yes, if you right-click or command-click on that block, and underneath duplicate, it says this block. So duplicate by itself means duplicate everything underneath here in the script, but duplicate this block means just duplicate the one block. Yeah, that's one of my favorite little features that I made Jens put in.
And you're right, I've never noticed it before.
Yeah.
You said it, right, that was good.
That's,
Another one of your complaints, right?
one of my complaints, exactly.
I love that you go to this.
I love
Yeah.
Jens because, I mean, he's really responsive. He's amazing. I mean,
Jens is the best programmer in the world.
yeah, he's tough. All right, you gotta add variables, okay, you have to add a variable. Color, level.
Right, but it doesn't do anything yet.
Another one, it's just size.
Right, so now what I
Okay, so now you got your two variables, you can pass it, all right? So you may have to see that as move.
size.
You gotta go one way before that. It's exactly like this. Turn this way. Turn left, step, and then you call. What you say? You say this shit out.
Why is it blank minus size steps?
It's just the negative size at the bottom.
Oh, I see.
It's 0 minus size is what's happening. There isn't a monadic minus block, so that's how you do it.
You could have had -1 time size.
Yeah, I could have said -1 time size. Yeah.
Level is the number of, yeah, the number of trees. But size is actually for, it's just like for, yeah, what you're saying. Size steps. Oh, right. So I
Okay, so we ready to see what happens if I run this?
No, we're not. We need a minute.
Okay. Everybody in TV land, you should know that what's going on is waiting for people to copy this script onto their computers. Oh, and I bet if I zoom back out, I'd be able to see what people are saying in TV land. That's the problem with being zoomed in.
Here we go.
So I'm going to show you what happens if I run this, which means I have to click OK, but don't panic. So here I'm going to go to the pen menu, grab tree, grab pen down, and now watch. I'm going to make a tree of level 5 and size 100. And when I run it, it does that. And it keeps going forever. So there's a bug in my program. There's actually 2 bugs, one of which is I don't want to be pointing to the right when I do it. I want to be pointing up. So when I call tree, I should start by saying point in direction up. And I should probably also say clear here.
By the way, I really like that it says up and it's the angle.
Yeah. So now, this is, oh, whoops, I should let it rotate. This is what's happening. Uh-oh, I'm in trouble. There we go. Here. Okay, so let's fix this problem. And the way I'm going to do that is, although I subtract 1 from level on the recursive calls, I never actually use level for anything. And to fix that, I'm going to grab an if block and put it around this entire program. Oops. And say if greater than level 0. Oh, and this is not plugged in. There we go. So if level is greater than 0, then do this. Okay, so here's the complete, oops, script. Ah, there we are. Wait, I'm going to zoom back down, see if that ding was somebody trying to talk to me, but I don't see a little thingo window. Okay, so I'm going to say OK. And I'm going to actually shrink this guy down a bit and make it easier to see. So now,
I got a quick question.
there you go.
We have a hat block in our block editor. It's too far over to the left. But we try to click on the move it, but it keeps.
You can't move the hat block. You have to move the other stuff in the block editor.
I removed the if, but that's good enough.
Just jiggle the if around and it'll, yeah.
You need a.
Sorry?
You go back to your code.
Oh, the code, yes.
So all we do is add the if.
I can't move the half block.
So now you can see the code and the tree at the same time.
It's O level.
By the way, this isn't a very realistic tree, but it could be made to be pretty easily. For one thing, I think that it gets small too soon. So if it said like 0.9 instead of 0.6, it would probably look a little more realistic. And the angles are spread out too much for a real tree. And also, real trees have branches halfway up the trunk, not just at the tippy top.
No, we know it's not a real tree.
Yeah. But this is the canonical example of a recursive program. And if you want to understand it, the absolutely only way to do it is by seeing that this tree consists of a trunk and a little tree and a little tree. If you try to do it line segment by line segment, there's 2 to the 6th power, whatever that is, little line segments, and you get lost very quickly. Mind you, kids have written tree programs in Scratch where they actually do keep track of all those little line segments, and the programs go on for pages and pages and pages, and they're completely incomprehensible. So it is possible, but this way it's easy. It's a tiny little piece of code.
I have to see if this is the truth, not that part. Do this, so slide the block over. Click here, slide.
Okay. I think I should sit down. Oh. And now I'm probably totally out of the view of the camera, and Dan has left the room, so tougho. But now is the time to take questions if anybody wants to jump in with one.
What is recursion used for out in the real world?
What is recursion used for out in the real world is the question. Fractals. So when you go to the movie from Pixar or something, and you see clouds or trees or a coastline or a body of water where the water is rippling, there's recursion going on in the programming of those things.
A seashell.
Yeah, seashell, yeah. So let me talk about the real world, since you asked that question. In the real world, there are 2 kinds of programmers. There are timid by-the-book programmers, and there are programmers who really understand what they're doing. Many of the former have been taught by their programming teachers to be afraid of recursion. Either because it's mysterious and incomprehensible, that's one reason, or because it is thought to be slow. I can't speak to incomprehensible, but it's not slow, that's a myth. What it does is let you write complicated programs quickly and without bugs, whereas doing it some other way, it's possible, but it's way, way harder. So in the world, there are recursive data structures. So sometimes you have a collection of things, and those things can be numbers or words or other collections of things. If you have a structure like that, and you want to look at every little thing or sub-thing or sub-sub-thing, it's a really good idea to use recursion. My favorite example of this, which I tell at the end of CS61A, which is our first class for majors every semester, is like this. There's a thing called a binary search tree. So imagine a tree like what you see on the screen, only upside down is how they usually draw them for some reason. And at the root is some number. And the rule is every number to the left has to be smaller than that number, and every number to the right has to be bigger than that number. So if the number at the root is 100, then the first one off to the left could be 80, and the first one off to the right could be 300. And then to the left of the 80 would be things less than 80. To the right of the 80 would be things bigger than 80 but less than 100, and so on. And this is a structure in which people put data to be able to look for something and say, is this number in the structure or not? And at the end of my 61A class taught in Scheme, I asked students to pull out a piece of paper and write a program to search for a number in the tree, taking advantage of the structure so you don't look at numbers that you don't have to look at, so it's efficient. And, you know, they do it, and I do it along with them, and it takes 5 minutes, and it would take 2 minutes if I weren't trying to do it along with them. And then I say, okay, the reason I gave you this example is 20 years ago, I gave this as a midterm problem in 61B, our data structures class, which at that time was taught in the C language. Now it's Java. And nobody, literally nobody, got that problem right. So I came into lecture the next day and said, you know, you guys had a little difficulty with this problem. Take out a piece of paper and write it in Scheme. And every kid in the class groaned because they thought they were done with Scheme, you know, now we're doing C. But they tried it, and I would say about half of them succeeded in Scheme, including, you know, people who had failed in doing it in C. So I showed them how to do it in Scheme, and they recursively, right? It involves 2 recursive calls, one for the left branch, one for the right branch. And the students said, yeah, but what does that have to do with writing it in C? And then what I did was I wrote it in C on the board next to the Scheme version, line by line the same except for the syntax. And the reason they had failed to write it on their midterm is that they were immersed in a culture of C programmers in which real men don't use recursion. And so they had tried to do it iteratively and with global variables, and they all wrote incredible messes. And if you're willing to remember big ideas like recursion, it helps you in dealing with recursive data structures, which come up all the time in the real world. So a lot of code in the real world isn't recursive that should be. But the code that's written by people who really understand what they're doing does use recursion. So that's all an answer to how is this used in the real world. Okay, other questions about recursion? Yeah.
So recursion just visually is something that goes, going on your example, the last step, it goes down, and then if you're just going to do one level, it'll be down, 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 down. So it just repeats.
Right. So
Lifting a pen, you can do that shape.
So a level 1 tree is you just go up and down the trunk. And a level 2 tree looks like a letter Y. Go up, draw a level 1 tree, ba-boop, draw a level 2 tree, ba-boop, and then back down. Okay? Yeah. And the reason we have this level thing is to know when to stop getting smaller and smaller. Although another way to do it, by the way, you could do without the level input. Maybe this is actually worth showing you. Okay. Instead of saying if level is greater than 0, I'm going to say if size is greater than some greater than 0 number, like 5. Okay? So now I'm going to forget about level. Move this over here. Oops. There. Forget about level. Move this over here. And then I'm going to delete the level variable. Delete. So now I only have size as an input. And I'm going to say tree 100. And I get this. So it keeps on branching as long as the size of a branch is at least 5 steps. So this actually makes it a little more realistic because the number of levels off to the left will be different from the number of levels to the right because the size shrinkage is different in the two directions. So let's see, is that true what I just said? 1, 2, 3, 4, 5 over here. 1, 2, 3, 4, 5, 6, 7 over here, right? So you get between 5 and 7, in this case, recursive calls. So it's not that there has to be something called level. It's that there has to be some way to say, we're not going to do any more recursion past this point. Okay?
I'm just trying out the different variable numbers, the different colors, so that I can see what the variables actually do.
So
This one I didn't change, this one I only changed.
They got
this
it.
one.
In other words, they got it, okay?
yeah, okay.
They got it. You got it now, right?
Now, recursion doesn't have to be for graphics. So one of the classic examples is called count change. Wait, what are we looking at? Okay, we're all going to come around. Oh, oops, I can't. Hang on.
There's one I'm gonna show you, the one you mentioned Josh yesterday. Josh has one.
Ooh, multicolored trees. Okay.
That looks like, what is that, Mikey somewhere?
Did I change the green and the blue? Is I changed that?
Change it to one.
Yeah. So if you're interested in colors, what you really want to do is have all the tree in brown except for the endmost little
Like Josh's
lines, which are in green.
tree, right?
Yeah.
I'll try to show him that today.
Okay, anyway. So here's a problem for you. Forget about computers for a second. I have quarters, dimes, nickels, and pennies. How many different ways can I make 37 cents? So figure that out. Go ahead, piece of paper or whatever.
I will now pause it.
Do you have to use them all?
No. You could use whatever, given any number of quarters, any number of dimes, any number of nickels, any number of pennies, how many ways can you make 37 cents?
And a quarter, a dime, and 2 pennies is the same as 2 pennies, a dime, and a quarter.
Right, yeah. So let me say it again for the
Combinations.
TV people.
I mean,
A quarter, a dime, and 2 pennies is the same solution as 2 pennies, a dime, and a quarter.
It'll go over it. That's why I did different color.
Oh, you quarter too.
So we're pausing now while people think about the count change problem. Go.
Quarter, dime, 2 pennies.
Okay.
Quarter, 2 nickels, 2 pennies.
While we're paused, what last soda do you guys want? Get another soda for the afternoon? Which would you like?
Drink water.
We have water fountains.
Sure.
Any soda?
Quarter, nickel,
Pepsi.
7 pennies.
Get it.
Okay, that's fine. Well, they had diet.
3 dimes, a nickel, 2
The
pennies.
dirt?
Yeah,
See, so-
great.
3 dimes, 7
The
pennies.
green is what
Drink
we
soda
had
here, guys?
originally, and
I'm
then
good,
now
thank
we
you.
changed to the pink.
Sure.
So wherever
The
it's
afternoon's
going,
until
it'll
5.
go
Come on.
to me.
2 more hours.
Do you have any more of
There was
the,
not actually one with green now because we changed that.
Right, 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 but,
No, I think that, I don't know.
the old values represent the green, and the new values represent the pink color.
So
So that's the change.
more,
It's
no?
gotten more in the, these branches.
Brian, what's your diet Pepsi
Significantly.
here?
What?
Do you want Pepsi?
7 up.
No, I'm okay.
Hey, go ahead, yeah, pass me 7 up.
7 up, come on.
Thank you.
Soda pop for you too?
Yes, please.
Uh-oh.
Well, you could do some pretty
oh, no, you have the
shitty
menu,
fake
you have the menu of everything as well, right?
Dan, you have an old BYOB.
Really?
Yeah,
Really?
Yeah,
Yeah.
it's more
What do you mean?
symmetrical than the
3-1
green.
beta?
See, 'cause
Yeah.
we see the green ends.
it's old.
Right.
It doesn't look exactly symmetrical, though,
2nd of
because
May.
here's the midline,
What?
right?
2nd of May.
This
Hmm.
still is,
I want browser.
Are people all doing that? Are people remotely all doing the same thing?
I hope so.
What do you want to do?
Well, here you are, browser.
You've hidden the window.
This is really obnoxious, so this is,
That's not it. That's not it.
how do we get the 37 cents
No.
using all this stuff? Oh, we're getting plus 2 pennies. Oh, gosh.
How many coins?
Yeah.
Yeah. Okay, tab.
How many coins?
Mm-hmm.
It's amazing. You just go on
We're going to higher functions now?
one.
Oops.
After this. This is the last recursion one. We're going to go to higher function.
Yeah.
Because I'm able now to visualize when we change those.
Right, 37 is a lot.
What?
You should have something. Parameters.
Scramble.
Yeah, well.
37 is a lot.
Okay, how many?
A bunch.
Not yet? Okay. It's just as well. I have to download the new BYOB. So that I can pull out the right example from it.
Getting the whole thing or just the files?
Just the files.
Okay.
But, okay, so where do you download into?
It downloads into here, which is the downloads folder,
Great.
and it's there. If you touch that, it'll unzip it,
Unzip it. Perfect.
and then it'll be in downloads. If you want to run from there,
It'll be in
I'm
downloads,
for
okay.
that. And you can go to downloads.
Oh, well, never mind. I can just go back to, wait, hang on. I can use this BYOB and say open.
Oh,
Stem down.
I like your pretty stuff.
up one. You're in documents. Go for it.
Without making pretty pictures.
Downloads.
Download.
Then you have to. Here we go. Right there.
Yeah.
You're lucky. Projects.
Yep.
What's the new one? Look at you. Look at you. Very nice. Okay, good.
Okay, gang, here we go. I'm going to hit the green flag. And Alonzo says, enter any amount of money in cents.
Wait. Come back to you. 3, 2.
All right. 3, 2. We're waiting for the tape.
For the Brian thing. Okay, and take 10 minutes and then we take all of it. Quick. Go.
Go. Okay, so I'm running this count change example, and Alonzo is saying, enter an amount of money in cents, and I'll show how to pay it in coins. So I'm going to enter 37. And you can do it with a quarter, a dime, and 2 pennies, a quarter, 2 nickels, and 2 pennies, a quarter, a nickel, and 7 pennies, a quarter, and 12 pennies, 3 dimes, a nickel, and 2 pennies, 3 dimes, and anyway, I can't keep up with this. But as you can see, there are a lot of ways of doing it, finally ending up with 37 pennies a couple of screenfuls from now. There we go. Cool, huh? All right. So this is an example of recursion that has nothing to do with graphics. I actually did some graphics to print out pictures of the coins. But the essence of the problem is as follows. Every way of making 37 cents either does or doesn't start with a quarter. So we can divide this problem into 2 pieces. How many ways are there that start with a quarter? That's actually pretty easy. There's quarter, dime, 2 pennies, quarter, 2 nickels, 2 pennies, quarter, 1 nickel, 7 pennies, quarter, 12 pennies. Those are the only ways. Okay? Now we can separately ask the question, how many ways are there that don't use a quarter? Right? Well, that's a new problem in a world in which there are only dimes, nickels, and pennies. So let's ask the question, how many ways are there starting with a dime? And then there may or may not be another dime, but there's at least 1 dime, versus how many ways are there that don't use any dimes at all?
Let me show you something cool. I made a picture of this. Keep talking.
Oh, okay, I'm going to keep talking. So the recursive procedure, the procedure for counting how many ways there are, is going to make 2 recursive calls. One that says, I'm using the biggest possible coin. And the other says, I'm not using the biggest possible coin. Oh boy, and here's Dan's beautiful slide.
Skip coin, use
Skip
coin.
coin, use coin. Right.
This is actually the,
Right. So this is all the different ways. For how much money? For 10 cents.
10 cents.
Yeah. But the important part of it is down here, which I'm going to scroll into. Whoops, up. Oop,
Yeah,
oop.
that's fine. You can hit Apple Plus. But that's
Yeah.
This is simple,
Great.
much simpler version of.
Yeah, so this is right here, the two recursive calls to count change. And instead of drawing pictures of them, we're just adding the answers. So let's say I don't use a quarter. So that's count change of whatever amount I had using all but the first coin. So the coins, remember, it's 25, 10, 5, 1, let's say. So count 37 cents using 10, 5, 1. And add to that, how many ways are there to make amount minus the biggest coin? So that's 30, so that's 12 cents using quarters, dimes, nickels, and pennies. Okay? So now what are the base cases? There's a few base cases, actually. If the amount is less than 0, there's no way to do it. If we have no coins to work with, there's no ways to do it. If the amount is equal to 0, here's the tricky part, there's one way to do it. Namely, no coins. Okay? But this plus, with the two recursive calls, is a great example of a kind of recursion that has nothing to do with drawing pictures. And yet, recursion is just the only plausible way to think about this problem. You know, you could do it without recursion. So if you were a recursion hater, you could have 4 nested loops, one of them about quarters, and then one of them about dimes, and one about nickels, and one about pennies. And you could have some global variable that you keep adding 1 to. And eventually you would get it to work. But it would take you a lot longer to debug than if you have this idea about dividing the problem into ways that use quarters and ways that don't use quarters.
You might be losing people when you say nested loops.
I might be losing people when I say nested loops. If you don't know what a nested loop is, good.
Don't use it.
Then you won't be tempted. Because the problem with the nested loop way is now what if I want to have 50-cent pieces, right? And $10 bills, you know, involved in my amount of money. Whereas this recursive solution takes the different denominations as an input. So I could have everything from $1,000 bills down to pennies in a list, and I can say, how many ways are there to count $50,000? And it would eventually, after a long time, come up with every possible way, including 5 million pennies. Right? That would be the last one I would think of. So you get a nice general solution that's tiny by using recursion. And the only reason I gave you this example is that it's not about graphics. Now, you know, kids love graphics, which is why in my version of count change, I actually draw pictures of coins. But in essence, this is just a problem about arithmetic. Right? The answer you get is a number, which is how many ways are there to do it. Okay, more questions about recursion? What?
1 minute left.
1 minute left before what? On the tape. Oh, and then we go to another tape. All right, so we have 1 minute for someone to ask a question.
How this is an infinite loop?
What?
Why does this run infinitely?
Why doesn't this run forever? Because of the base cases, which, uh-oh, here's somebody's mic on.
It's Baker. He's got a question.
Here. Yes, what? Hello? Okay. What's the question?
Yeah, there's just the screen.
Oh, I see.
Yeah. You wanna see mine?
Oh, okay. Oh, look at that. You're seeing a blue mesh. I wonder why that is.
That's what doesn't go with that.
No, it's stupid software.
0 minutes.
Request control. I am in control of the screen. Okay. Now if I go to Scratch, now can you see? Nope, you can't.
Okay. 0 minutes of the tape.
0 minutes of the tape. Okay, well,
The reason is each recursive case makes it smaller and the base case caches it. That's the answer.
yeah, so, right, each recursive case is a smaller case.
Caches both of them.
Yeah. I wish I could solve this video problem.
Number of coins, then reduces the value, but keeps the number